Yeah, thank you, Jess, and thanks the organizers for this great workshop so far. I've been asked to talk about IFU data in general terms. So this talk is going to be, or this tutorial is going to be composed by two parts. The first part is going to be an overview of IFU data, and the second part is going to be an example of a software that I find particularly helpful for exploring IFU data. So, what is IFU data? Well, IFU stands for Integral Field Unit, and sometimes you can also find the references to IFS, which stands for Integral Field Spectrograph or Integral Field Spectroscopy. The idea here is that with this instrumentation, you have it's a combination of imaging and spectroscopy. Here is an illustration of a IFU data cube in which you have a galaxy in the field of view, and then the data cube is composed by three dimensions, three axes, two spatial axes, and one spectral axis. So for every single position in the sky within the field of view, you also have a spectrum associated to it. And this is very helpful because you can also, so if you have a galaxy like this, you can ask, okay, what does the spectrum of the galaxy look in this part compared to this part, or compared to the center, or compared to that object here, etc. And also you can think about, well, you can extract information in another way. So you can also go to a fixed wavelength and ask, okay, how does the field of view look like at that particular wavelength? And you have an image. So it's very powerful for astrophysical purposes. Sometimes the references about pixel, spaxel, and voxel, this is terminology, is a convention. When we usually refer to pixels, it's about an image. So only an image with two dimensions. So element of that image is a pixel. And a spaxel is it's an element of a data cube. So in the two spatial axes. So the difference between a pixel and a spaxel will be that the pixel is just a value in the image. A spaxel has a spectrum associated to it, so has several values for each wavelength. And finally, I wanted to comment on the voxel concept. The voxel will be the volume element of this data cube. So it will be only one value, but it has to be a specified position in the sky and a wavelength. How does IFU work? Basically, you need to always go through an spectrograph to be able to produce a spectrum. And the way to do that in the IFU concept is to do it in independent regions of the sky. So you can know that a spectrum is associated to a given distinct region in the sky. There are several ways to do that. Here are three examples with lenslets, fibers, and image slicers that can be used to finally produce the data cube. I want to emphasize in this first part of the tutorial that what you get from the telescope is not a data cube directly. You get a spectra in a two-dimensional CCD array or a detector. And then you need to do post-processing to go from this situation here, which is a spectra in a CCD, a two-dimensional spectrum in a CCD, to a data cube, as the one that we were looking at before. Some examples of instruments that have IFUs. Here's a non-exhausted list. I just added the first one that came to my mind when I was doing this slide. I wanted to emphasize that several spectrographs have IFUs, even though they might not be so commonly used by our community in particular. So GMOS has a small IFU of 5 arc seconds times 7 or 3.5 arc seconds. The others that might be designed as an IFU from the beginning, like manga. It's composed by IFUs of 32 arc seconds in diameter, given with 130 fibers of 2 arc seconds each. So the IFU of manga looks like something like that. An hexagon with a lot of fibers inside, and for every single position within that hexagon, you have a spectrum associated to the fiber that is closer to that. The limitation here is that the size of the fiber is 2 arc seconds, so you cannot resolve, especially resolve things smaller than the fiber size. But it's very powerful for doing a large survey like manga has done. In this particular tutorial, I'm gonna now focus in the second part. I'm gonna show data of this particular IFU, which is Muse, which is the larger in the available with these large telescope apertures. In contrast to manga, this one has more than 100,000 spaxels compared to the 130, and each spaxel has a pixel size of 0.2 arc seconds, so 10 times smaller than the fibers of manga, and a field of view that is much larger, 4 times, more larger than the manga field of view. Quickly, what does Muse look like? This is Muse in the telescope. Here's a person doing some fixing in the instrument. Muse is an instrument composed by 24 IFUs. So that's why it's so large. There are 24 independent IFUs that are used to combine and slice the field of view of the instrument. Briefly, what the instrument does, it reshapes the field of view into a rectangular region like this, then divides the field of view into 24 channels, and each of those channels are going to go through a different IFU, integral field unit. In order to slice the field, there is a field splitter, which is several mirrors like that. And then once you are in a given channel, there is a image slicer like that on the top that slice the channel into 48 different slices, different regions. Each of those are going to go through a spectrograph and produce a spectrum. So 48 spectra times 24 channels. So you have a lot of 2D spectra out of the full instrument. This is how one of those single images in the CCD look like, with 24 2D spectra, and you have a spectrum, of course, in the vertical direction, and in the horizontal direction, depending on the slit, you will have different position in the sky, depending on how is the slice located within the channel. Of course, once you get to this point of having the 2D spectra of all of the channels and all of the slices, it is convenient to reformat the information as a single data cube. It's much more convenient to work with the cube rather than to work with this 2D spectra in a CCD. And that's done typically as part of the reduction process. IFU data, as it's going to be a data cube, can be saved as a standard FITS file with 3 axes, in contrast to an image which has only 2 axes. So here I show you just a part of the header of a Muse data cube. So it has 315 pixels in one direction in the sky, 319 pixels in the other direction, or spaxels, and almost 3,700 pixels in the wavelength direction, and that's going to be our data cube. In the next 10 minutes, I'm going to give an example of the software I use to analyze data cubes for a quick inspection, mostly. And this is a software I recommend. It's called Coolfits View. Oops. It's developed by Thomas Ott, and you can find the documentation here in this webpage. You can download directly the binary file for Linux and Microsoft Windows and Mac OS X, and it seems to be well supported as far as I know with other users. So now let me show you one example, or well, I'm going to stop here to answer possible questions regarding the concept of the IFU before going to the second part. That's I cannot see the chat. Sorry. Yes.
Yeah, I think so. That's nice to pause. Actually, I like the idea of pausing right now. So for anybody who has any questions about the first part, it sounds like Nicolas is going to move to more of like a demonstration of Coolfits View. Go ahead and raise your hand now, and I'll wait about 10 seconds while people contemplate. Maybe they have questions now, but I think that was, and we can wait to see if anybody raises their hand.
Yeah, I also wanted to say that you can also use other software like DS9. As long as the data is well formatted in a fixed file standard, DS9 should be able to load it as a data cube as well.
I know what I remember when I was a graduate student, so a long time ago, we used KViz, I think, which is like a radio astronomer package that was developed by Australians, and I remember really liking that one too.
Yeah, Casa, I think, right? Oh, no. I haven't used that one.
Karma, maybe Karma? Was it called Karma? Like the full package might have been called Karma.
Okay, yeah, there might be others, of course. I am not so familiar with that particular one. Yeah.
Yeah. All right, I'm not seeing any hands, so we might as well go into Coolfits View.
Coolfits View. Okay. Coolfits View here. So, all right. So here I have a data cube of a Muse data. So I'm going to open it with Coolfits View, and I'm just executing the binary file that I just downloaded from the web page. It asks you to select the the extension, and I'm going to select the data extension. This is the variance extension for the Muse data cubes. So you select data, it loads, and here's the data cube. So yeah, you can, similar to DS9 and other software, you can select the cut levels, and you can see a field of view. This is 1 arc minute by 1 arc minute. There is a key stroke that you can use to go and get distances on the given the WCS. So 60 arc seconds by 60 arc seconds. You can also use it to measure distance from one source to another, etc. And this is just an image in a single wavelength, which is given here. So in this panel, you find the position in the sky, and in the bottom panel, you find the spectra associated to the pixel or the spaxel I am located. In this case, this is spaxel here. Let me just go to this source. So here is a star, and you see the spectrum of that star. I can move the mouse and trying to find a galaxy here. So I found a galaxy, and that particular spaxel has this particular spectrum. You can also do some larger apertures. So you can, let's say, circular aperture of 3 pixels radius will look something like this, and you have a better signal to noise spectra of that particular source because you are summing up more spaxels. You can sum, you can take average. In this case, average and sum is the same. It's just the normalization factor. Or you can take median, and the shape of the spectrum that you get in that particular aperture changes a bit. Now, this is here is the full spectrum, but here I see only the wavelength associated to this array here. So that particular wavelength, around 7,000 angstroms. Another thing that you can do is take. So I want to show the field of view. If I move in different wavelengths, this is how the data look like. Some wavelengths are cleaner than others. because when you are in a sky line, for instance, everything is much noisier. When you're in cleaner part of the spectra, you get cleaner quality of the image. You can use this to look for sources that show up in one single wavelength, or if you want to integrate more wavelengths, you can do that on the fly here as well by taking an average, for instance. This takes a little bit because it's doing the summation on the fly. And now it's going to show an image of the full cube collapsed along the wavelength direction. And which is very useful because you will see fainter objects like this. So now we see more objects that were not so obvious before in a single wavelength. And you see the arc that look much brighter, and you can even see fainter arc segments that otherwise are not so obvious to see. In the context of Coolfits View, you can also select different regions, different spaxels to produce the spectrum that is shown on the bottom. So for instance, I can select a square region like that, and that's shown in the green part here. I can add this to the green part, and it's going to sum that spectra at class that. And I can keep doing this for reference purposes, for instance. I can also do regions not necessarily square. I can add a single spaxels like that, or I can remove spaxels with a keystroke that I will let you know later. It's in the documentation in the web page. Yeah, you can use that for reference purposes, or whatever purpose you like. In the final 3 minutes I have, I'm going to show you one characteristic I like a lot about Coolfits View, which is the fact that you can produce maps of, you can produce kind of, let's say, pseudo-narrow band filter maps. We know this field. We have been using this data to study one particular galaxy in this field with the gravitational arc. So we know that there is a galaxy here, right on top of the arc, but it's not so obvious when we look at this particular integration. If I place the cursor here, I see the galaxy because this is oxygen 2 emission from that galaxy. Now I can do a pseudo narrow band filter centered in this O2 feature with a keystroke, which is the C keystroke. It's in the documentation. I can point to that later. And this is an image now, it's a line map centered on that particular wavelength range that I selected in the bottom. Many sources have continuum or lines. Many sources have flags at this wavelength. But now I can take a continuum reference level right on the side of that to subtract to this and just get like emission around that particular wavelength. So I'm going to take this as a reference, and this is what you get. This is a narrow band continuum subtracted image. It's a line map. It's a bit complex because it has this minus this part here integrated. And this is the galaxy that we studied in one of our last papers on gravitational arc tomography. So this is oxygen 6 galaxy. You can resolve more or less the kinematics of the galaxy. You see how the emission line shifts, especially the centers of the lines. And if we come back to the original full map, there is the arc here, and you can go for -2 associated to that particular redshift, which is this one here. This is the -2 doublet associated to the galaxy I just showed here. And you see that the -2 is strong when we are close to the galaxy. And we move along the arc, and it gets weaker and weaker until a point, you cannot longer see the -2. But that's how we can particularly resolve not resolve, have a coherent mechanism true map in the CGM of a single galaxy with several contiguous positions. If we go to the north arc segment, there is no mechanism 2. It should show up somewhere here. And it doesn't show up in this particular arc, but it does show up here. And there are other features besides the ones I just showed that are worth exploring for the Coolfits view. Many options I haven't even tried myself, but there are some spectral and analysis options that you can use. I'm not going to do it now because I'm out of time, but I can show you some other capabilities of this particular software. I wanted to finish saying that this is a very nice software for exploring the data, but not necessarily for complex analysis. I mean, there are some analysis that you can do, but if you want to have a more complex analysis, I recommend to do that with a script and reading the data cube with a Python package or whatever other software package, and accessing the data cube as a NumPy array or equivalent to do more complex analysis. But this is a very good software for exploring the data. So that's it.
Thank you, Nicolas. I absolutely love IFU data. It's just so rich. And this is such an amazing tool for at least like getting that kind of first idea of like what is here in this field. And I love the example that you chose in particular. And so, yeah, that's just really, really remarkable. What a beautiful image too, with that lovely arc there. So I am going to suggest that you moderate the discussion, and that we just that we can hang out here and discuss and ask you questions. And so yeah, let's open up the floor to questions about IFU data or just in general about this field. And while people are thinking of them, you can just raise your hands or unmute since, you know, there's not a huge number of us. But what was so the galaxy redshift, I did like a quick by eye thing, was like 0.73, and that you were showing that was on top of the arc. What's the redshift of the arc? It's like, what is it like? It must be like 0.8 or something like that, because I saw the magnesium 2 up a little further.
No, the arc, it's a much larger, higher redshift. It's a 2 point something, I forgot.
Oh, 2 point something. Oh, yeah.
The arc itself, the emission of the arc. So
yeah,
here's the arc. Well, let me. Yeah, so this is a feature, a big significant feature of the arc. I forgot what was carbon 3, or I don't remember. But yeah, you're right. The galaxy I showed is 0.73, and then magnesium 2 that I was showing is a 0.73 as well.
Right. Yeah, I just wasn't sure what the arc was. I knew it must be higher redshift. I thought those absorption lines that I was seeing on just the arc itself were something else. But anyway, cool. Very cool. All right, more questions for Nicolas in this discussion. Especially, I'm interested maybe in hearing from simulators that might want to try to make their own data cubes.
I have a question. Well, this is for Nicolas and also other people. What softwares do you use to, well, if you observe diffuse emission, you really have to remove the diffuse background or scatter light or any calibration imperfections perfectly. Do you use any post-processing software for this? And sometimes I worry about comparing faint emission data from different different integral field spectrographs. I worry about the absolute surface brightness calibration comparisons.
Yeah, that's a very important concern, and actually, I think it's very difficult to remove all of the artifacts. I want to emphasize here that even in this reduction that we believe it's good for our purposes, you can still see some of the different illumination patterns of the image slicers in this particular instrument. And that might also be true for other IFUs. So you're right, it's tough to calibrate the low surface brightness in the large field of view. It's not trivial, and there are software to do that do a good job. But you always have to be careful in that particular respect.
Yeah, this cube that you gave an example of, is that something that's delivered to you like from Muse after your data is taken without any kind of additional post-processing on your part, or what's the source of
this one has been reduced by I forgot, I need to check the header, but I believe this one has been reduced by a member of our team and has been post-processed to remove some sky residuals using a very nice software that works very well for Muse data called SAP. But it hasn't been particularly look at this low-level flux variation that you can emphasize here when we do this summation.
Cool.
So the Muse data cube that ISO is going to give you from the archive is similar to this, but probably slightly lower quality than this one. But you can also do better quality reduction if the analysis needs that, particular for faint low surface brightness objects.
So Cameron, what do you think? Can you turn Trident into an IFU?
Yeah, I think so. I think there's definitely room to expand Trident's functionality to be able to produce data cubes like this.
Yeah, the noise here, as you can see, it's not trivial. You see all of these patterns. What we have done as a first attempt to reproduce simulations, like we can start with a idealized spectra, like normalized spectra, then we multiply by the continuum, let's say a quasar or a gravitational arc, and then we basically just, one way to do that empirically is just to have an estimation of the noise, empirical noise in a data cube, and add the spectra on top of that, rather than simulate the noise, because it's not a Gaussian noise anymore. And it's going to be different if it falls here or if the source falls here. But it will be nice to think about that for future. Yeah, and another point from Trident, thank you for commenting on that. For Trident, the sidelines, as far as I understand, these are like pencil beam sidelines, right? It will be good to think about how to extend that to extended sources with different emission.
So, there's been discussion with Evan Schneider and Kate Rubin to try and do extended sources with Trident with existing functionality, and we're all putting together some modifications to the code, so that should be for like down the barrel observations. We should have that kind of functionality parameterized in the next month or so. But yeah, definitely that's a stepping stone towards something like what you're proposing here with the IFU datasets.
Excellent.
The future of both observations and simulations. I noticed there's some KCWI users here too. I don't know if any of them want to comment on similar tools to look at like KCWI data, or how it looks different, or anything like that. I've never looked at KCWI data or Muse data myself. I have kind of data envy as somebody who just does the pencil beam stuff.
I think we all use Coolfits View.
Yes, we all do.
Okay, so Coolfits View is kind of state of the art. I mean, it's really amazing.
I was wondering if anyone is involved in some either data reduction or post-processing or analysis tools that will be useful for all IFU data taken for all instruments, like some standardized reduction package like pipettes. Just like I mentioned, and I guess everyone is worried about its absolute comparisons of the surface brightness values.
Yeah, I wonder, is anybody, I don't think Prochaska is here, but you know, he does this pipette thing.
Yeah.
Does that have, is that IFU compatible pipette yet? Do you know? I mean, that's kind of the idea behind that software, as far as I know. Oh, Kate's here. Perfect.
Pipette can pretty much reduce a KCWI cube, depending on the data a bit and the setup. Not all of the setups are in the pipeline yet, but it's pretty much there.
Mm-hmm. And then, I mean, you would need to like import some instrument specific parameters, but in theory then, if it can do KCWI, it can do any IFU, right? Like as long as the instrument properties are put into the...
I will say that not all have the same design, so I don't think it's so straightforward to just change parameters in a code. You have to change the workflow.
Sure.
But other, yeah, in the sense, Manga IFU is different than GMOS IFU, and Muse concept is different than KCWI concept. I'm not sure if you can have I think you will need a new recipe, completely different recipe for each instrument, but perhaps another expert in instrumentation, well, an expert in IFU instrumentation can comment.
What would be amazing too is if you could use, okay, so you have like your simulation. Okay, so you run Trident on your TNG, 300 simulation. You've used all of these publicly available tools and you've got your data cube, and then you can put that data cube right into Coolfits View and look at it side by side with the actual Muse field. I think that that's a cool thing to look forward to. All right. More questions?
I could add that just for manga data, there's a website where you can explore manga data and access it called Marvin. If anyone is interested, sorry, I'm not. I'll just put it. I'll put it in Slack later.
I appreciate that.
But I mean, it doesn't allow you to do as much as Coolfits View in terms of interacting with the reduced data, but it does show you, the velocity profiles across galaxies and many derived quantities. So that might be useful and fun and it's very easy to interact with the galaxies and pick out your favorite galaxies. So I'll put that in the Slack.
Awesome. Thank you. All right. Well, if there are no more questions or comments, this is a good time to wrap up for the day with 6 minutes to spare. I don't know if they're here, but thank you so much to all of the tutorial leaders today. Today was, I think, just an absolutely exceptional tutorial day with 3 true tutorials. And so that was really fun and informative.
Thank you all, and thank you all the organizers for this amazing workshop so far.